Welcome to this explainer. Let's just dive right in, shall we? Today, we are taking some of the most intimidating music production jargon and translating it into pure, actionable clarity. And we're going to do it by tracking one single sound's epic journey through a modern recording studio. If you have ever felt completely overwhelmed by the deeply technical language engineers throw around, well, you are in the exact right place to finally make sense of it all. I mean, have you ever looked at a massive mixing desk and wondered what on earth all those knobs actually do? Before your favorite track even hits your streaming playlist, that audio signal has to navigate this incredibly complex maze of hardware and software. It's really not just a simple matter of plugging a microphone into a wall and pressing record. There is this vast ecosystem of equipment, and honestly, understanding the terminology of how a signal flows through that ecosystem, that is the ultimate key to mastering music production. So here is our roadmap to break down these dense technical concepts into 6 manageable steps. 1. Studio signal routing. 2. The patch bay puzzle. 3. Analog to digital conversion. 4. Navigating the DAW. 5. MIDI and controllers. And finally, 6. Acoustics and interference. Section 1. Studio signal routing. Our signals journey kicks off right at the heart of the studio, the mixing desk, where we have to figure out exactly where this raw sound needs to go. That brings us to our first crucial piece of music production terminology, routing. Think of routing as the ultimate traffic control system for your audio. You are literally directing the sound exactly where you want it to travel. Without proper routing, a killer performance simply goes nowhere. Every single switch and knob on a recording console is placed there to help you make deliberate choices about the path that signal takes, whether it's heading to a multi-track recorder, an external effects unit, or straight into a musician's headphones in the vocal booth. Which leads us perfectly to this next vital term, the bus. A large professional mixing console might have 24, 48, or even 64 of these things. The term bus essentially refers to the internal cabling that runs horizontally across all the vertical channels on a desk, carrying audio to a specific destination. So instead of plugging and unplugging physical wires behind a heavy desk every single time you want to group sounds together, the bus gives you a super convenient built-in highway. Now, I know these internal pathways can sound kind of abstract, but think about a real-world equivalent, like an actual city transit bus. Just like a city bus picks up people from various stops along its route and takes them to one final destination, an audio bus picks up signals from various channels, say an entire drum kit spanning channels 1 through 8, and groups them all together. Then, boom, you can turn up or down that entire drum kit with just one single control fader. Honestly, it's an absolute game changer for producers' workflow. Section 2, the patch bay puzzle. Next up, our audio signal encounters a piece of hardware that usually intimidates beginners, the patch bay. But really, it just acts as a central hub to save you from a messy nightmare of tangled studio cables. The crucial point here is understanding a concept called normaling. See, because certain devices are almost always connected together, like your mixing desk outputs straight to your recording interface, the patch bay uses a clever internal switching system to link them automatically. In a full normal setup, the top output socket connects to the bottom input automatically, no front cables needed. But if you plug a cable into either socket, that automatic connection breaks instantly. Now, in a half-normal setup, plugging a cable into the top output does not break the connection. It's kind of like a Y-splitter cable. It lets the audio keep flowing down to its normal destination while letting you bleed off a perfect copy to send somewhere else entirely. Pretty smart, right? And that brings us to the insert. Let's say you want to take our audio signal, send it completely out of the mixing desk into a sweet piece of external hardware, like an expensive vintage compressor, and then bring it right back into the exact same channel. Well, you'd use an insert. It basically creates a seamless loop, featuring a send and a return, letting you process the audio midstream without losing its spot in the mix. Section 3. Analog to digital conversion. For our analog signal to actually get inside a modern computer system, it has to be translated into a totally different language, the digital domain. And there is a fundamental difference between these two worlds. Analog audio is this continuous, constantly changing wave of electrical voltage that perfectly mimics the continuous changes in air pressure we hear as sound. Digital audio, on the other hand, well, it knows absolutely nothing about smooth, continuous waves. It literally only understands discrete digits, zeros and ones, hard binary code. So we have to bridge that massive gap. We do that using a process called pulse code modulation, or PCM. Imagine laying your fluid analog waveform down onto a piece of graph paper. The horizontal axis represents time, and the vertical axis represents amplitude or loudness. The digital converter meticulously measures the amplitude of that sound wave at incredibly fast, regular intervals along the horizontal axis. Then, it assigns a specific binary value to every single vertical measurement it takes. By snapping all these rapid-fire sequential pictures, the system digitizes that fluid wave into hard-readable data. So you might be wondering, exactly how fast do these snapshots need to be taken? Well, the Nyquist theorem dictates that to accurately capture both the top and the bottom of a frequency wave, your sample rate has to be at least double that specific frequency. Since the upper limit of human hearing is roughly 20 kilohertz, the standard sample rate chosen for CD-quality audio was 44.1 kilohertz. To put that into perspective, the system is taking an astonishing 44,100 discrete snapshots of the audio every single second. Crazy, right? And building on our graph paper analogy, when we talk about bit depth, we're talking about the vertical axis, basically how incredibly accurate each one of those amplitude measurements can be. If you're using a standard 16-bit depth, the computer system has exactly 65,536 possible values to choose from when measuring the amplitude of each snapshot. That precise combination of sample rate and bit depth is exactly what allows a standard compact disc to hold 74 minutes of high-quality audio. Section 4. Navigating the DAW. Now our fully digitized signal has arrived inside the computer, specifically into the DAW, or Digital Audio Workstation. What's deeply fascinating here is how the software directly replicates the physical hardware we literally just talked about. The terminology shifts a bit, sure, but the core concepts are completely identical. Those physical auxiliary knobs on the mixing desk, in the DAW, they become your bus sends. Those hardware patch bay inserts, they become empty software slots where you drag and drop your digital processing plugins like EQs or digital compressors. It's like having the power of a massive, multi-million-dollar hardware studio right at your fingertips, but you no longer have to worry about tripping over heavy physical cables all day. Section 5. MIDI and controllers. Sometimes, though, our signal isn't actual audio at all. Sometimes it's performance data generated by a performer, which takes us into the world of MIDI. Now, MIDI, musical instrument digital interface, doesn't actually send sound. It sends performance instructions like note on or note off. And while those traditional 5-pin DIN legacy cables are definitely still kicking around, modern studio controllers are on a whole other level. They increasingly rely on computer networking, local area networks using Ethernet. If you step up to a gigabit Ethernet connection, like 1000 base T, your studio controllers can handle massive amounts of data at lightning speeds of 1000 megabits per second. And honestly, all that network speed is vital when we talk about continuous controllers. The MIDI protocol has 128 specific controller numbers assigned to different performance parameters. For instance, CC number 1 is always your modulation wheel. CC number 7 handles the overall channel volume. CC number 10 is for panning your sound left and right, and CC 64 triggers the sustain pedal. When a producer manipulates these, they are sending precise, continuous streams of messages to shape that digital sound in real time. It's what gives electronic performances those realistic human nuances. Section 6. Acoustics and interference. Finally, our signal is fully mixed, completely processed, and ready to be heard. It converts back from digital to analog, travels out of the studio monitor speakers, and actually hits the physical space of the room. This is where the absolute laws of physics just take over. As sound waves bounce off the studio walls, floor, and ceiling, they start interacting in the air. If two positive sound waves collide, they combine to create a much louder summed value. We call this constructive interference. But if a positive wave and a negative wave collide, they destructively cancel each other out. Literally, your perfectly mixed massive bass line could suddenly sound overwhelmingly boomy or just completely vanish into thin air, purely based on where you are sitting in the room. This wild acoustic phenomenon creates what we call room modes. Basically, room modes are specific sonic frequencies that perfectly match the exact mathematical dimensions between parallel walls in your studio. When a sound wave hits that specific resonant frequency, it creates a standing wave. It just bounces back and forth continuously without decaying naturally. Because of this, acoustic engineers have to meticulously calculate these room modes so they can build specialized bass traps and install diffusers. It's absolutely crucial for preventing those specific frequencies from awkwardly building up and muddying the sound in different corners of the studio. So, we've tracked our signal all the way from the mixing desk routing through the complexities of the patch bay, digitized it with pulse code modulation, processed it in the DAW with high-speed MIDI controllers, and finally unleashed it into the acoustic space of a studio where interference takes hold. Now that you understand this journey and the precise terminology of the modern studio, it kind of naturally makes you wonder about the future, right? As we move further and further away from heavy physical cables and deeper into high-speed digital networks, what is next? Will virtual reality become the next revolutionary leap, the interface where producers physically interact with their DAW in a 3D space? Maybe you'll be the one to invent it. Thanks so much for joining me on this explainer, and I will catch you on the next one.